So welcome everyone to the NAC lecture series. It's my pleasure to introduce Tom Erbe, who, if you've done any sort of computer music in the last 20 years, you probably heard his name. Soundhack, his software, is probably one of the first things you learn if you start doing spectral manipulations of sound. Tom Erbe has worked in a lot of places. He studied at the University of Illinois in Urbana-Champaign. He's worked at Mills College, CalArts, and UCSD, where he's right now. And he's moved between software and hardware throughout his projects. So I've got a long bio, but Tom just wanted to do the first talk, so I'll just let him go over it. Thank you, Tom.
Thanks. So I'm going to talk about this new reverb that I've designed, as you know, most of this talk. But I should preface it by just giving a little bit of my history. I started writing computer music software around 1984, 1985 at UCSD. This was, I was a research assistant at the Computer Audio Research Lab there in the mid-'80s. And at that time, that was really sort of my finishing school. This is where I learned a lot of the techniques that I've used. After a bit, I really realized that I was in it for the music. And the things that I wanted to do were not things that would make me great papers or would make me a lot of money, but they were things that I could program that would get out there, and what would come back is interesting music. Because my motivation for all this is really hearing new sounds and hearing, getting the excitement from the new sounds. So this has always been what my work has been about. When I left UCSD, I went to Mills College, which was really refreshing because a very creative environment that had zero budget. We had no money, barely for computers. I had gone from a place with a $1 million mainframe to a place that could barely afford a Mac II. So what this freed me up to do is work. You took the computer you had, and you wouldn't think about fundraising. You wouldn't think about getting grants. They weren't available, or you were too small or too weird, really, to get them. So Mills College allowed me to focus on my work and just develop software. And working with musicians there, it allowed me to develop software that would get used. So when I first got Soundhack running, and I had Alvin Curran using it for sounds in his piece, immediately I saw where things were relevant. And so, to me, it's not just making software, it's not just getting the software out there, but it's getting the software out there to musicians and seeing how they react. And but my other connection is with the academic computer music research environment, where people are making really weird sounds or really experimental sounds, where people are learning new things about sound. And what I've enjoyed doing is sitting between the two worlds, where I can absorb the research papers, where I can look at things, and then I can put them into a commercial environment where people will actually use the software and get new stuff out of it. So, if you look at Soundhack, if you look at all my plugins, this is really the focus my work has taken. I say around 98, I started writing plugins for VST and audio units, and I've made about 20 of them now. And I may be about to stop, but I won't talk about that yet. I'm also an audio engineer. I've worked as a recording engineer for new music. I've done around 100 CDs or so, and what I found was as the digital studio environment developed, things were getting quite boring. You were getting compressors that were very generic, very clinical, delays that were very clinical, and you weren't finding the sort of imaginative things you saw in old analog approaches. So this was my mission, to bring back some sort of interpretation of effects, to not just make the clinical canonical effect, but to make something that encompassed some of my own aesthetics, that looked at the history of that effect. And this is very much where this reverb's coming from. When I looked at reverb, I'd previously been involved in developing this delay device, the Echophone, for a company called Make Noise. And Make Noise asked me to do a reverb. It was not my idea. I had always thought of reverb as sort of a wash, a faceless wash that you put on things to make things more lovely or smoother or gel together better in the mix. So I thought maybe there's not much to do there in reverb, but I thought it might be nice to take a sort of academic approach to reverb. There's not a lot of text on reverb. There's not a lot of, there are a lot of secrets there, first off. And so it's hard to actually know what people are doing in, say, a Lexicon, an EMT, or even Pine Reverb. So I felt from an academic approach, I could start studying this and maybe find some of the secrets and get to the point where I can publish some of these, skirting whatever legal things I need to skirt, but it sort of reveal what these secrets are. I thought there's a real need in the computer music textbooks for this chapter. So my first approach was not to think of the effect that I wanted, but just to learn everything about what everyone else has done in reverb. And this was my same approach when I developed the Echophone, the delay line. I took delay and I just went through the history of delay from tape delay on and just looked at the devices, looked at how they worked, looked at how they sounded, and try to wrap the things that I really found compelling into one device. Okay, so reverb. I thought about replicating a space. I mean, this is what reverb is. You're taking a space and you're making that space for people, and then they can put their instruments in it, and you get diffuse reflections coming back. An obvious answer to that is a convolution reverb, where you're essentially sampling the space. You're sampling one position, you're making your impulse, you're recording the impulse response, and then you're playing that back for each sample. And that works really well. But it doesn't really lend itself well to parametric changes. For me, what I wanted is something that's a performance instrument where you have knobs, where you can change things, where people can, find spaces that aren't essentially real. So I discarded the convolution approach and I started looking at the approach, the delay line approach. And there's a whole class of reverbs, and I'll be showing you the different ones, where you take a group of delay lines and you make things complex enough so that it acts almost like a real room. But then I got to think, well, what is it that we want reverb to do? And I came up with very few things, really. But one of the main things is to give an instrument sustain, to sing in a room and have the room respond back. So for me, this was the number one thing I wanted my reverb to do, was to just sustain a note, to extend a note, and to give it some different character. Beyond that, it needs to shape the overtones. It needs to give some sense of a difference from the original sound. So your sound goes into the room. What comes back is related, but it's different. And that difference informs you about the space. And it allows you to react to the space. And when you sing in that space or play your instrument in that space, you change the way you perform. So to me, it's part of the interaction. And last, it gives you a sense of location. This I don't need to do anything about. No matter what comes back, no matter how strange it is, it'll still give a sense of location. You'll still feel I'm in this space, even though if it's some very science fiction type space, you'll find that consistency, and this is what reverb gives to you. So I have three very sort of loose requirements for what I wanted reverb to be. And I should say that I found myself at this point sort of at the same juncture. It's sort of similar to the music concrete electronic music juncture, where I'm really sort of falling on the electronic music side of things, where I'm looking at sort of a pure definition of reverb, and I wanted to elaborate from there. So getting more specific, I wanted certain qualities in my reverb, and I wanted all of these things to be variable. I wanted a variable echo density, so that the higher the echo density, the more complex the room. The lower the echo density, the more the room is a simple thing with parallel walls, or even a sphere where you get a single reflection. I wanted to make some sort of coloration variable. I did want to allow for a smooth exponential decay. Most real rooms, or rooms that have good reverb acoustics, have a decay that's exponential, and there's a way of achieving that. So this was one design goal. I wanted to allow for a sense of clarity. Clarity really means that when someone performs with the reverb, you hear the person, you hear the original sound. So the techniques are to either make your reverb dark, or make your reverb sparse in the beginning and dense later on. So this quality had to be there for me, for people to perform with it. I wanted variable diffusion. Okay, this gets into what diffusion is. Diffusion is how complex the echo is off the hall. So, loosely. And so I wanted to make the ability to have things more complex or less complex. That is to go from scattered echoes to many, many, many echoes to the point where you cannot distinguish where they fuse together. And then finally, almost all reverb, real reverb or artificial reverb pulses and has sort of a dominant echo mode that you'll hear. So I wanted to get some control over this pulsing or repetition. Okay, so the research goals: make a good reverb. I mean, this was number one. Make it sound good. I didn't want to make it sound like a space. I just wanted to make it sound good. And what's sounding good? Well, my context here is people here will be playing through a modular synthesizer. They'll be making certain kinds of tones. It has to work with those tones. How do I tell? Well, I have to use my own ear, but I also have to use a lot of people. So I've sent this thing out to a lot of different people. They've listened to it. They've critiqued it. I've gotten the vaguest terms possible, like it sounds colored, or it sounds bright, or it sounds crispy, or it sounds muddy. Part of the process of finding out whether something sounds good is to, have people develop their vocabulary a little bit so you can find out what it means when something's colored. First they say, oh, of course everything is colored, That's ridiculous. Of course, it's not the same sound you put in. Yes, I know that. That's the other lesson is don't get frustrated. Develop some sort of language and find out what people are hearing. If possible, get in the same room with them and, see their reaction. That as soon as you play your example in front of other people, you learn exactly what you're hearing right away.
Could you say more on develop your language? You mean develop your ability to understand what people mean with these vague terms, or do you mean teach people a vocabulary? Or don't say it's colored. Say.
Well, do you hear the low frequencies sustaining longer?
Right. So
how long do they sustain?
Like more engineering terms?
In more engineering terms.
Is that what you mean?
Yeah.
So when you say develop a language, you mean the language that you're
develop a common language between the people.
He's
Yeah.
inviting them.
Yeah.
So yeah, I mean, we'll start talking, and it helps if the worst thing is sending things out and then getting emails back. Because then you have 5 emails back and forth, and then people get frustrated, and, you know, you never know what people are saying. So better is if they're in the studio with you. Otherwise, a phone call after they heard something, and then you can sort of quiz them. What did you hear here? Try this kind of sound, and what do you hear? You know, and get a little more detail, really. And sometimes, yes, it is you developing your own understanding of their terms. So, okay. So, then the next thing is to look for a place to broaden the algorithm to get more interesting spaces. What can I put into Reverb that is going to make maybe impossible spaces? And then finally, one of my goals was to put everything on knobs. I was sort of sick of reverbs where you would switch between plate and hall and room. And, you know, where you would be basically, even though these, like a Lexicon reverb is an algorithmic reverb, they've sort of turned it into a sampled reverb by changing things by switches. So I wanted to remove the switches and just have everything flow continuously from one thing to the next. A further difficulty is that when you make a module, a piece of hardware, if you put more than, you know, right now I have 7 knobs on here, and that's considered rather extreme. And sort of like, only a real boffin would use that many knobs, but you start looking for places where you can combine patterns, where you can place ranges, and finally you look at tuning the knob so that the user's guided to certain ranges, so that the most interesting sounds are always found. So there's a lot of work there. Okay, so previous work, and let me jump to this slide first. If you go to my website, you'll scroll down. It's a WordPress site, and there's a section on Reverb. And I not only have all my PD patches there, but I also have all these references here. Okay, what you'll find, if you look through the literature, is you'll find some older academic papers. You'll find Jean-Marc Jot's stuff, which is wonderful. Newer stuff. But then you'll find also some commercial stuff which is hidden. And the place you look for commercial research is patent searches, mainly. Now, a lot of it has sort of risen to the foreground. And you'll find papers like John DeToro's paper, Effect Design, where he basically reveals what the Lexicon Reverb is doing. So a lot of the resources are out there, but it takes a little bit of searching. The academic papers, there's a bit of a disconnect from the commercial reverb, so you have to sort of make that connection. And the connection is really through the patents like Chris Moore's paper, through John DeToro's paper. Jean-Marc Jot's going in a different direction altogether, but you know, a lot of ideas in there, but they're not all connected together. The other thing I should point out is in the DAFX book, which, do you guys use that as a textbook? There is actually a really great section on Reverb, which covers a lot of ground. Okay, so what you find is there's this sort of development of ideas and topologies throughout Reverb. We'll start with Manpreet Schroeder. He started with a network of all-pass and comb filters, and more or less like this: 4 comb filters or delays with feedback, followed by 2 all-pass filters or delays that are feed-forward and feedback. The comb filters are tuned to things like 30 milliseconds, 44 milliseconds, more or less the reflections in a room, the size of a room. The all-pass filters, though, are set for very short times, and what the all-pass filters add to this network is they tend to fill in a little complexity in between these primary echoes in the comb filters. So let me go to a quick demonstration of an all-pass filter. So here I've done a little PD patch, and what I have is a chain of 4 all-pass filters. These all-pass filters are at 3.5 seconds to 12.7 seconds, so each one is a little different. And when we hear something like this drum sample, hopefully this is not too loud. I'll turn it down to start. Is that too loud out there? Okay. So now when I turn up the gain on the all-pass filters, you hear this sort of smearing of the sound. Do you hear that through the speakers? And turn it up quite a bit. Let's put some percussion through here. So as I bring the gain down. So there's the original. And there's through a chain of all-pass filters. Okay. I'll stop that. So this is, this is one of the keys to modern reverb, is what Manfred Schroeder found out, is that using all-pass filters, short time all-pass filters in the range of 1 to 15 milliseconds, it does a lot to fill in the echoes. And it's just not using one all-pass filter, but using a chain of them, so that every echo from an all-pass filter branches off to more echoes that are now the compound of those times. So you get this quick sort of diffusion. Now, does this emulate a room, a concert hall with many, different shapes? It maybe sort of does, but it's definitely not physical modeling. It's finding something that acts a little bit like real acoustics, but really have nothing to do with it. The danger with all-pass filters is that they're based on a feedback mechanism. So if you turn the gain up too high, they will start ringing. And though if you look at their spectra over the whole term of the all-pass filter, you'll find that it's a flat frequency response. What happens is your ear focuses at short periods at a time. And so you hear the pitched portions at moments. So you really need to consider your ears and consider, your own perception of pitchedness from the all-pass filters. And this is your guide to how long you can make the all-pass filter and how much gain you can give the network. Okay, so again, Manfred Schroeder's technique was to take the large echoes and put them in parallel, have them all feed into a summer, and then into a chain of all-pass filters. And what you get is something that doesn't actually sound that good at all. But it sounded great for 1962. This is the beginning. I shouldn't say that. That's so mean. Okay, so we take that same percussion performance. So what you hear, you still hear these primary reflections really distinctly. It's not complex enough. The all-pass filters are doing a pretty good job smearing it out, but not enough. Okay, so further developments. We take James Moore's reverb, which is actually fairly similar. He has an all-pass filter, a single all-pass filter. And this runs into a number of parallel comb filters, but his innovation is adding a low-pass filter in each comb filter. So now this network, this now approximates more what a hall does, where you don't get everything back that you send to the wall. Hopefully, so the filter, it gives you a nice sort of wooden wall. It's still somewhat simple, but I do want to play this example. I will say that Andy Moore also added another thing to this reverb. So this is actually a simplified version of the reverb. But what you'll hear is it does sound more like a real room. Because now you have a progression of darkness. Things get darker as time goes on. Because right in the comb filter, right in the echo path is the filter. So every time you go through the filter, it gets darker. And it acts like a real room that way. And it also gives you the ability to have clarity. That is, now the new sound can sit above the reverberated sound, because the reverberated sound has a limited spectrum. We have more spectral roll-off as the reverb proceeds. Okay, the other thing Andy Moore added is the notion of early reflections, and this is what I didn't add here, where he actually added an FIR filter with several taps, or you could think of it as a multi-tap delay line, which approximates the early reflections in the room. And this does quite a lot to make it more complex and more realistic. This was 1979. At the same time, in the commercial world, we have Chris Moore with the Ursa Major space station. And this is really, it's a crazy diagram. It's not such a crazy design. I couldn't think of how else to draw it, but what he has is really one delay line with many, many taps, from 47 milliseconds to 250 milliseconds. So what he says, what he wanted to do is just increase the echo density really quickly. And this more or less does that. And then it has one feedback path for all of these delay lines. So with that single feedback path, all the delay lines are now being fed back into each other, so we get even more complexity every time we go through this structure. So this improves things greatly. And then finally, on his output, he did the same thing Andy Moore did, and he added a early reflection network. Now, it's on the output. This is convenient from an engineering point of view. But yes, it is the early reflections. But yes, you can put this on the input or the output. It will do the same thing. What these are a set of reflections that allow you to model different sizes of rooms, different kinds of rooms. And if you look at an Ursa Major space station, it has push buttons to trigger different sets of early reflections. Okay. The other big innovation, Chris Moore's big innovation, was all of these delay lines are modulated. And by doing that, we no longer have tones building up. So we can actually now get more gain through this network without feeding back on any prominent tone. And he also added full EQ sections in the feedback network, which in his original device, all of the EQ is analog. So it also had a bit of saturation, natural saturation in there. Okay, so this sounds quite a bit different. Let me play the percussion again. Okay, so you should hear two things. One, you should hear that modulation. There's sort of a pitch shifting effect. It's sort of a chorusing. And for a lot of things, that makes for a richer sound. It's no longer a real sound at all, but it has this sort of nice texture to it. The other thing is that things get complex enough later so that it actually sounds more or less like a real room. We have actually enough echo density in this reverb to sound like a reverb. Okay. Meanwhile, split efforts. In 1971, Michael Gerson came up with this structure, which is several parallel delays going into a matrix. And in 1982, John Stoutner and Mylar Puckett came up with the same idea. The problem was that Michael Gerson published his stuff in a magazine called Studio Sound, a magazine that you generally only saw in the UK. And really wonderful articles, which I might have linked to on my website. We'll see. If you need a copy, I'll get you a PDF. But he really just walks you through this. He was really talking about using, linking multiple analog delay lines together and using analog matrices to sort of, have this cross feedback. And what we have now is 4 delay lines going into a matrix where everything feeds back into everything else. The other thing, this is a unity gain matrix. So we can actually control the feedback. This is the Hadamard matrix. And this idea can be extended. This is a 4x4 reverb. You can have 8x8, 16x16. You can build it up as large as you can compute. 4x4 is actually fairly simple. Now, the thing about now that we have this feedback matrix and we have that, and we know it's unity gain, we can actually have this reverb hold a tone. You can turn up the gain to 1, and it just sustains, which is really nice. You couldn't do that in Chris Moore's design, obviously. The earlier designs were sort of separate comb filters, which each have their own independent feedback, and they were also, if you got those to sustain, you would just hear sort of these bad echoes. But this actually, rooms don't have infinite reverb. They don't hold a tone forever. But compositionally, if you're performing with this, you can play a violin note and, press a switch and suddenly have that tone held in your piece. And this is a really nice thing. The other thing, because you have unity gain, now you can cut the gain down below unity. So you cut the gain to 0.9. And your output, your decay, is exponential. So this now acts like a really nice room. So this is what you get with the unity gain network. So one decay control point, which is our gain for feedback. And Mylar Puckett in his design, he added a low-pass filter before the delay line so that you could add some sort of room damping. Now, the PD patch I made is not Millar's design, but it's Michael Gerson's design. You can find, if you open up one of the reverbs that's built into PD, you can find Millar's design. So Rev 2 tilde and Rev 3 tilde are Millar's designs. But this is Michael Gerson's, and what will you notice? You'll notice that it actually doesn't sound that. It sounds very, very colored, yeah. It sounds quite different than the Gerson reverb. If we give it a little white noise, or this is just a burst of white noise that's filtered, you can still hear ringing, and you hear sort of these individual reflections. You can increase the damping. So these are one-pole filters in the feedback. And the difference here between this and, say, Schroeder's design is that, and the difference between Chris Moore's design is really the simplicity. We're only using 4 delay lines for this reverb, which is not much at all. Even the Schroeder design used several all-pass filters, which are really feed-forward feedback delay lines, and a number of delay lines. Moore's design and Chris Moore's design used many more delay lines. If you take this design and make it into an 8x8, suddenly you get enough echo density, so it starts to sound like a real reverb. It starts to sound rich. And yes, the other thing you'll notice with this network is if we turn up the feedback gain, and I'll turn down the output, don't worry. We can now put a tone in it, and let me turn the damping down. And this will just sustain. And then when we bring the gain down, we get a nice exponential decay. So one nice thing about this closed loop design is we can really control how the sound decays. So I'm going to move forward a little more quickly. I'm spending too much time on each of these examples. But this was what I needed to do to develop a reverb, is study everything that I could and see what people were doing. And the other part of building these patches was not for this talk. Building these patches was for me to actually hear what these reverbs sound like. I mean, you read a paper about Schroeder's reverb, you might find a C-sound unit that says it does it, but you don't really get into what it's doing, and they may have implemented it wrong, so it really helps to implement these things yourself and sort of figure out what makes them work well. So, okay, so Lexicon, this is actually a pretty important design, and you really should get into the DeToro paper to look at this. But when we look at it, it's often described as a figure 8, but really what it is it's a single loop. And it's a loop with 4 delay lines, very much like the Puckett-Gerson Stoutner thing, but we only have one path. It's much more simplified. Sound comes in, goes through here, up there, there, and back again. So with this one loop, we can now have unity gain. If we put these decays at 1, we can sustain forever. But there are a few more things added here. The all-pass filters are now seen all over the place. We have a chain of 4 all-pass filters coming into the structure. We have all-pass filters in between every delay line. And so this puts all-pass filters in feedback. So as things go through this loop, we get more and more complex echoes and more complex short-term echoes. So things quickly turn into white noise. And you can see the sidebands just grow off of tones, and we hear a very quick wash of sound. The other thing that David Gritzinger added was these all-pass filters are modulated, and that is the time on the all-pass filters is slightly modulated. So the short-term spectral, resonances are now shifting around. We have a sort of a phase-shifting chorusing going on these 2 all-pass filters. So, yeah, I'm spending too much time. Let me play this example. This is the Lexicon reverb. You've probably heard this one. And so the percussion through here. So it finally sounds like a reverb. Or what we think is what we want out of a reverb. And what I'm starting to think is it's really, you need to achieve that echo density quickly. If you don't, you get these prominent echoes. You need to be able to modulate time-based things so that you don't get any one frequency building up. And it helps to have a single loop structure or even a complex matrix loop structure so that you can manage the gain. So this is where I went with my own reverb. So I started with the feedback delay network reverb. And I added an all-pass filter at the beginning of each delay line. So this gave me immediately much higher density. And sound enters all 4 delays at once, so it hits all 4 all-passes at once. And once you have one pass-through, things get pretty complex already. So I put an adjustable gain on the all-pass filters, so I could actually take them out of the network. And why do you want that? Well, sometimes you do want things to sound like a multi-tap delay line. Often you want a quick percussive hit to sound like a rattle. You know, other times you do want it to sound like a room. So I wanted that adjustability in there. So the other thing is my most expensive thing, is to make every delay time variable. And what I wanted was a single knob that controlled all the delay times and allowed me to change the size of the room quickly through a single modulation. So for this, you need to do some sort of interpolation. You need to make a fractional delay line, and you need to think about whether you want to use parabolic or linear interpolation. And eventually you know, in my case, I was implementing it on a microprocessor. So eventually you find out that your microprocessor can't do any more than you want, and you have to change your gain, you know, so that happens several times. And yeah, room size should go beyond reasonable sizes. So right now, my reverb goes from a room that is 4 inches by 4 inches to 400 feet by 300 feet, or 4 by 3 to 400 by 300. And it does it on one swing of the knob. You don't hear that. I mean, when you turn it to 4 inches, you don't think, well, that's a 4-inch room. I mean, what you hear is something different, you know, and you might use it in your music. And that's what I was thinking, that, okay, there's this vast range where people hear reverb, but there's this other range where it turns into something else. And I was really interested in having that something else be there as well. Okay, so I added a few more things. If you know Gordon Luma's piece, he's talking about this idea where rooms change size as you're playing them, and he's basically modulating reverb devices. And a lot of when I put this example up, all the composers come out and say, no, I have a piece where I'm modulating reverb size too. And then there's lots of pieces where people had this idea of rooms that just change size. And so you can do this by just sort of continuously changing the size, like on this knob. But what I wanted to also happen was to have the multiple room sizes appear at once. So that a room we may be this wide, but suddenly the room gets to be 10 feet wide. So these walls start materializing. And what I'm talking about, of course, is to use a sort of granular approach where each grain has a different room size, and I can change one room to another. And those room sizes can be chosen randomly with a center and a range. So I changed all the delays to granular delays. Yes.
Does your frequency get treated the same or do you segregate for different sizes?
Well, these delay lengths are all chosen to be somewhat prime of each other, or rather I tuned the basic delay lengths so that I didn't have any repeating echoes. And I looked for closest multiples and tried to make them, and then as you add up two of them, that it's not within 5% of another two of them. So I used a spreadsheet to sort of find the right delay times to work with each other. Once I got the basic delay lines down, then then the granular stuff goes around those delay times, and that's just randomly happening. So there is a granular depth in there, and if you just turn it a little bit, things will just be changing a little bit around the size, so your walls are just sort of going like this. And then there's also a speed of modulation, which, it could be very slow. So you might hear resonances, especially when you're feeding back. You'll hear resonances coming in and then suddenly shifting out. So this is the kind of thing that happens. The other thing, if you're running the granular speed very quickly, resonances won't build up at all. You can now bring up the gain very high, and you'll get this, the granular changing will interfere with any sort of resonance. Did that sort of answer your question?
Get that second part.
Yeah. So now that I'm doing this, if you've done any sort of stochastic process like this, especially in a feedback loop, you'll see now that gain is somewhat unpredictable. Yes, you're throwing a random element in there. You can figure it out on the average, but if you're doing things slowly, you now have a real source of feedback. So the next thing to put in here are sigmoid functions. You need to have some sort of clipping protection in there. Or you need clipping protection plus short time limiting. Something like that to just allow you to bring the gain up and not have things explode. Or have things explode, but make them sound, frightening rather than terrifying. I don't know. You want to have some control over the process. So this was the next thing, but when I did that, I found, okay, decay can now be higher. I can now set decay up to 1.5. And now I can have this whole thing sustain on its own. So this, then the other stuff is practical stuff. Just things that make it more performable. An output filter on a reverb actually makes a huge difference. And if you can quickly, with one knob make things darker or brighter, this is great. If you add 3 filters, if you add like a 7-band parametric EQ on the output of your reverb, it's nice, but no one wants to turn all those knobs, especially not in the modular realm. So what I had to do was tune a 3-band filter, low, mid, high, find crossover points that worked, and have one knob that does that or that. Sort of, make it quickly brighter or darker. Once I added that, lots of complaints about the reverb went away. People love just suddenly making this a really bass Jurassic Park sort of reverb, or to just focus on really bright stuff and take away all that darkness that might obscure instrumental stuff on top of it. All time parameters have to be clocked so that if anyone's doing anything that is on a constant metronome, they will want their granular rate to go at the same time, or a multiple or a division of that clock. So that has to be built in. And then pre-delay and early reflection is necessary to really make things real. First, you need a pre-delay to emulate that moment when sound hasn't hit the wall yet, to have some separation. This is one of the primary things you put in there to give the room size. If it takes a long time before you hear the first echo, you think you're in a big space. So that's simple, but you have to add it. And then the early reflections, this is just taking multiple taps off of all the delay lines, not just those 4 outputs, but take multiple taps in each delay line and bring them out. And you need to choose it so you're not doing any obvious comb filtering. You still have to pay attention to that. But what it does is it actually just gives you quick, early complexity. Okay, so I should demonstrate my PD patch. And yeah, this is the other thing. When I make plugins, when I make hardware, I always implement everything in PD first, or you can do this in Max, of course, but PD is my language, so. And I spend a lot of time just sort of tweaking things and trying things out. So this is where this reverb started, and here's, I think, a concert hall patch, so. Here I can have a long sustain. And you hear the granular modulation in there. Here I can have more than sustain. So I can get sort of this modulated feedback tone. And here I have this quick tilt knob that I can quickly adjust the sound of that. And then I can also send the whole thing into feedback. Turn it down first. Okay. Go back to our room. So, I mean, the idea was to go beyond a reverb to allow that sort of feedback, and one of the inspirations was actually the Chris Moore space station, where a few people from studios told me, well, they work really hard to get these so-called ghost tones out of the Ursa Major, that you could get ghost tones. And I was like, what are you talking about? So I found that Chris Moore's reverb actually had a little more than 1.0 gain in the feedback section. And if you turned it up in circumstances, you'd get these sustained resonances. And this is one thing people liked getting. So for modular synth, I thought this has to be there. I have to have feedback. Okay, so once I get the software together, then I needed to put it into hardware. I developed this for the ARM processor, and specifically the STM32F4. Did I put that up there? Yeah, okay. And there's a guy named Eric Brownbaugh who makes these circuit boards for like $25 or something, and a lot of my students have put them together. And basically it's a codec, a Wolfson codec, an ARM chip, and then you take this interface to one of the ARM development boards, and you can just program this and try things out. So a nice little cheap prototyping environment. The ARM chip has multiple A to D converters on it, which are all 12-bit, so they're really low resolution. But what you use them for is your knobs. They're still low resolution. What they do is they inject noise into every one of your algorithms. So the first thing you find when you download things here is that things sound horrible. You know, basically, white noise is being injected, pops and clicks are being injected. So the biggest problem with putting things onto embedded hardware is to smooth out the parameters. So what you need to do, I don't know if anyone's doing embedded stuff here, so are people interested in this? Okay, well, what you need to do is you need to do a lot of deglitching of that. So the first stage, you find that the A-to-D converters can run fairly high speed, and you can put a interrupt callback on them. So you do simple averaging low pass to start with, and that gets rid of a lot of the noise and gets you up to about 10-bit, out of a 12-bit converter. Then after that, you need to put some hysteresis in the control. That is, you need to make sure the control changes enough before you register it. Because with any delay algorithm, if you're changing the time a little bit, it's just going to inject noise into your delay, and especially a feedback delay system, it's going to mess it up, pretty badly. So you need to sort of hold that control. And then finally, the result, when you get a reading off the knob, it might be a knob. Yeah, that goes from 0 to 1, say you normalize it. But you might put that into an exponential parameter. And now you need to actually low pass your exponential parameter. You tune that so that when you turn the knob, it doesn't sound like it's going, that you're getting all sorts of Doppler. You want people to quickly change the speed and not have to go whoop, that kind of thing, which you might have heard on some delay lines, and you definitely hear on the Echophone. Echophone was done on a much cheaper processor. So it's a matter of tuning those two filters and hysteresis to keep it in control. That was the main engineering task with this. Otherwise, programming embedded processors, it's all C code. You're actually using GNU CC. It's very easy. The code pretty much goes straight over. The one negative thing is your processor is 180 megahertz. So it's pretty slow. It's the only program it's running, but you'll find that, you just put too much in there, and it didn't take me long. It took me like 7 pages of code, and then it ran out of time. So you'll find quicker ways to do things. You'll get smarter. You'll be clever, right? But yeah, the achievement here was, if I put this into feedback, you'll hear it more clearly, was to just take the size knob and make it fast, but not make it Doppler. So, and when people want to modulate this, they're going to want to connect an envelope generator on here or a trigger, and they're going to want to have things go very, very fast. Or, if they want slowness, they'll put their own slew in there. I know this is entertaining. But does that make sense? So this was the main thing, was, yes, embedded processors aren't fast, easy to get things over. To get the initial software over, it took me a weekend to get the first thing I got over was the Lexicon Reverb, because it's a much simpler structure, and that took a weekend, and then I put my own in there. The difficulty is dealing with glitching. The other difficulty is scaling the knobs. What you might think you want to do is you want to put all the interesting stuff in the center of the knob and have a nice even range around each thing. But what you find is everyone turns all the knobs all the way up for the first thing. So you actually want to concentrate the interesting stuff on this side of the knob, and put the subtle, maybe you can say aggressive stuff, subtle stuff. So you sort of do this nice sort of yin-yang balancing of your knobs, right? And you take it to the users, and this is what I found. When you send it out to the users, they complain about things, and you find out where they're setting their settings. And it may be that they just need to tune the settings differently to get the nice sound. So you think, okay, I want a straight exponential range on here, but you may have to change that. Yes. Not in a modular environment, because it's all linked to control voltages. Yeah. I mean, that's nice. But the other difficulty is that you do have to get things into one rotation here. And it's only 12 bits, which is really only 10 bits, so you have 1,000 values, really. In some cases, you should put things on 2 knobs. And probably with the echo thing, it needed to be. Okay, the other thing is combining things. Like, I combined diffusion and damping into one knob called absorption. Because, if you look at engineers or musicians, they don't know the difference anyway. And all you're really doing, and when you're talking about diffusion and damping, you're really talking about acoustician terms for what happened in a room. Do these things change in a room? No, they're sort of static parameters that are there for a room. So if you put 2 different knobs, it sort of doesn't make sense. Or you can have the freedom to combine these. Anyway. So, more to do. And yes, there is more to do. And the one thing I need to do after I make this hardware is to actually make software. which is a sort of interesting way to start doing things. But I need to make a plugin after I make this hardware. The plugin will have more options. I do want to have the early reflections spatialized so that you get a more sense of envelopment. I want to think about other types of processing I might be putting in the feedback loop, not just the granular delay, but, certain kinds of frequency shifting and pitch shifting. I want to think about, pre-computing the gain so that I get more control over it, especially things which are stochastic. And the other thing is to integrate convolution techniques, specifically to look at diffusion and early reflections and use impulse responses for the small components within the reverb. And then also look at connecting multiple rooms, and for the software, why not make a GUI where people can just build their own topology and try things out, where you can go from a Schroeder to a Moore type reverb and actually hear the different effects. So, did I finish on time? Yeah. God, questions. Are there any questions? Yes.
Well, I guess I was saying, since your advice was see how much you can pack into a microcontroller, what kind of compromises did you make when you started running out of
okay.
horsepower?
Well, the first thing is to choose a microprocessor, which is really difficult. I mean, there's so many out there, right? So the first thing I was looking for was one that does floating point quickly, because I knew this would be key, and it's not just the clock rate. Previously, for the Echophone, I used a fixed point processor that has a 16-bit word size and 32-bit accumulator, and I had to do lots of double instructions to get enough precision to do anything. And double instructions eat up your clock cycles. So suddenly you have half the number of instructions. So the ARM, the F4, has a floating point processor that does most things in a single instruction. Multiplies certainly, accumulates certainly, divides definitely not. But you can do most things that you need to do. Then the next thing for reverb is memory size. So you needed to find a way to connect to memory that's cheap. And what you'll find is each embedded processor supports a different type of memory device. And so you have to do a lot of shopping through Mouser catalogs to find out how much those things actually cost. And so what we found was that this ARM processor costs like $11, and the memory it talks to costs about $4, which was reasonably inexpensive. And of course, all costs get multiplied before they go to the market. But it made it affordable. And what I didn't want to do is make a module for that no one could afford. There's another processor called the Shark, which is much, much faster, has a lot more embedded memory, and it actually costs just about the same amount. But what we found is that it takes so much power that it would be the only module you'd be able to put in your modular. All right. So there are a lot of different choices, and so I got together with an electrical engineer who was looking at those sort of issues, and I was looking at software issues, and they're saying, well, how little memory can you work with? And then the other thing is some embedded processors don't have ADDs built in, others do. So there are all those kind of things. There are thousands of parts though. And the other thing that saves time is a community. The fact that Eric Brownbaugh built a board already and I could just order it off the website and solder it up, that saved me a lot of time. The fact that a lot of people are working on ARM and I can get a free compiler, that runs on an OS 10, believe it or not, that's great. So this is a big consideration when you're developing. The other thing about the Shark is it does cost, I think, $1,000 for the development tools, which someone could do $1,000. University of California can do that. But since I did this as a commercial project, I can't do that on UC money. But, so I had to keep things cheap and affordable. And why? It's just to make sure the final product is affordable. I think it's going to cost around $500. it is expensive, but, that means the dealer buys it and maybe Tony Rolando's coming later. Don't tell him I said that. I'm not supposed to announce it, but the markup for the dealer is about 100%. So the dealer buys it for $270 and then sells it for $500. Parts on this altogether are maybe $100. So that's the profit's somewhere $150. So it is a good amount of profit. But you don't sell a lot of these. That's the other thing. The Echophone, I think they've sold about 800 so far over 2 years. And that's considered a really huge success, But it's not a lot of people developing it either. We keep it a small business. Everything's made locally, all that, and, artisanal modules, right? Yes?
How do your samples sound to the actual device compared to the PD simulation?
Not as good. Well, yes and no. I mean, there are some things I had to do in the math that were cheating. I had to simplify the granular structure. Other things sound better simply because you have knobs to immediately change things and you're reacting to things quickly. So you can quickly tune into a sound that's better, but I'd have to say, I'm using more precision on PD. I'm actually, things are a little more finely tuned. A lot of things have to be in tables here, so I don't have to ever call log or power or any of that. But it does suffer a little bit.
Did you stumble upon something that was interesting that you didn't expect when you went to hardware?
Yeah, well, one thing is just playing with different saturation algorithms has a big effect. So if you model an arctan saturation or you model x minus x squared over 6, these all have different sounds. And I started with the cheapest saturation algorithm, and I really kind of liked it. It got sort of aggressive and noisy. The other thing you find is the sort of sounds that you would put into this, they're different than, my percussion tracks. So you start tuning the algorithm to suit those sounds. And finally, I had no control over the analog front end and back end. So that introduced a little bit of distortion and compression that added to the sound. And I just sort of had to tune the algorithm for that.
You mean the A to D and D to A's that were on the card you were using?
No, there's just the op amps before and after, and then the wet dry mix is done with a VCA, which is not perfectly linear. Yes. Because the format is constantly changing. So over the last 3 years, we've gone from VST 2.4 to VST 3. We don't know which one's being supported, really. Do you have an answer for that?
In Studio One and Sonar, they've switched to VST3, sort of.
Yeah, so it's like complicated, right? Yeah.
They've brought the overlay. Yeah.
And if you're programming in Juice, can you do a VST3?
It has a simple VST3 wrapper where you have every VST2 featured, but it doesn't have support for easy sidechaining that most hosts support, where you target a channel, you select a channel and you say, this is the sidechain channel. Because in VST3 you have that where you can name the channels and the host will be aware. No, Juice does not have good VST3 support yet.
VSTs have changed a lot. Audio units are constantly changing. They keep calling it the same spec. But what you'll find is that certain features you use will just disappear. If you did anything for Pro Tools, it's all garbage now. All your RTAS stuff you have to throw away. And you have to use AAX, which also involves a big license, I think. And everything went from 32-bit to 64-bit for, just so people can have big sample libraries, presumably. And that means recompiling everything, maybe rewriting all your graphics, and it's a different process on Mac and Windows. So I have about 20 plugins out now, and mine are in basically 5 different versions. RTAS and VST on Windows, RTAS, VST, and Audio Unit on Mac. And so 100 different plugins I have to recompile. And now I have to recompile them for both 32-bit and 64-bit. So I have to recompile 200 pieces of code when I want to do an update. So now if you teach, you generously get the summer off to do research. And so I have to take a whole month of that summer, a third of that summer, just to keep things the same. I'm not doing anything new. And then I do research, and then I want to write it. I want to document it as well. Otherwise, no one knows about it, right? So you have to give up something. So I'm thinking plugins are just forget it. It's, oh no, I'll find a way to do it. I mean, I'll fund a graduate student, right?
Do you sell them or leave them?
I eat both. Yeah, I do a lot of them as a part of my programming class. So what I did for several years is every year I would program a plugin during class and sort of start from the beginning and work on, and always put things in like, here's how to do modulation, here's how to do low frequency oscillators, and sort of that's class. Yeah, no, I mean, usually the plugin gets big enough, but that it's too complex for the student to just grasp, but it works well as a class because they see things go from a simple idea to something complex. And when it's complex enough, it actually looks like a reasonable plugin that you actually want to use. Internally, this is hugely complex, but to the user, it's 7 knobs, which are kind of usable. If it only had 1 knob, that'd be not very fun. Yeah.